like everyone to please give a warm welcome to Doug Hampton. He is currently with Trane Corporation. He used to be with Alvine Engineering as their premier commissioning agent. And he's been doing a lot of work with Brian and myself from kind of here, some of the representation here in the Midwest for the Association of Controls Professionals with their certifications. So he's been a good friend of ours here at the college of mine for about 6 or 8 years now. So.
Thank you, Robert. I appreciate it. Thanks for the opportunity to come share some things with you today. And I had an opportunity to work with Robert in the field good many years. How the college talked him into coming here, I have no idea, but he has done a tremendous amount for this college. So he deserves a clap for sure. Thank you, Robert. So Robert asked me to come in tonight, and I couldn't really decide what I want to talk about. I've done commissioning, I did data analytics, I was a control guy forever, I was a service guy, I'm a thermographer. So I took each one of these guys I do day classes on, so I thought, I'm going to try to take 3 days and pack it into an hour if I can. So if there's anything that I go over too fast or I need to explain, please stop me and I'll explain it. I made Robert erase this so I could draw some stuff up here. So we're going to jump right into commissioning. And the title, it's a working title. I wasn't quite sure about that. So commissioning, we're going to start with that from a building commissioning perspective. What is building commissioning? It's a systematic review, if you will, of the design intent of a building. How it's designed, we check it, functional test it to see if it performs based on the design intent, correct? We're going to talk about the commissioning process from start to finish. The cost benefits of commissioning, there are some, quite a few actually. Using analytics with commissioning and from your perspective. Data, it's all we hear about all day long now. Metadata, data. We have all this data, what do we do with it, right? And then tools, I'm going to go over some thermal imaging at the end with some pictures and videos and whatnot, some things I've seen over the years. So, commissioning. There's a lot of different things to a lot of different people. We can do commissioning in new construction, existing buildings, and typically in existing buildings we call that recommissioning if a building has been commissioned in the past, or retro-commissioning if it has never been commissioned. The retro-commissioning can be called a lot of different things: energy audits, energy assessments, mechanical assessments. Just depends on who you ask and what the objective is. So the typical commissioning process: pre-design, design, construction, and occupancy. The ideal process, as we've all been taught through the commissioning world, is from pre-design through occupancy. But we all know that that's a pipe dream. It typically happens in the construction and occupancy phase. Usually the commissioning authority is hired late in the game as far as I'm concerned. We always should try to strive to get in here, but that rarely ever happens. I've had maybe one out of hundreds of commissioning projects that started in that aspect of the design phase. So what does commissioning cost? 20 cents per square foot, $1.50 per square foot. How do we figure that out? It's all based on size of the building, complication. A data center, a lot more tech, is going to go for $1.50, or something smaller that's repetitive like heat pump system, it's probably going to be a little cheaper. Operating cost savings, now this is a pretty round number, 8% to 20% below that of a non-commissioned building. It's pretty typical. I'd like to think that we have a lot more potential that way, but you have to remember with commissioning we're looking at the design intent, how it was designed. So we try to stay within that design intent. I don't know how much of this you can see, but these are some of the non-energy benefits of commissioning. You look at the new building. This is a big one right here. Change orders, first cost, those kill a job every time. You get the commissioning guy involved, guy, girl. That's going to lower those costs and equipment life and a bunch of other things. The big takeaway here, though, is in an existing building. Look at how that impacts the equipment life. So there's lots of things outside of financial benefits that commissioning can do for you. So let's jump right into the data. And again, I'm going to go over a lot of stuff here, so if you, anytime you don't understand what I'm saying, please stop me. So as a commissioning person, we need to use the data we have. Building automation systems take all that building information and they put it together for us in a nice package. They have graphics, data, logs, trends, whatever. We need to utilize that as much as possible. How do we do that? CXA is short for Commissioning Authority, and controls vendors work together prior to and during commissioning. It's paramount. Got to work together, because if you don't, you're going to end up with a building that doesn't work right. Doesn't work well. Control vendor determine what data will assist in commissioning, because you can tell a control guy all day long, I want you to do all these data logs for me, and if you don't get along, you don't tell him ahead of time, he's going to say, no, that was not in my scope. So you want them on your team, for sure. That is a big one right there. Owner-driven commissioning. I don't care who hired me. I don't care if it's an architect or an engineering firm. Regardless, I work for the owner. Any commissioning authority should, if they know what they're doing, right? So what's the best way to get the owner involved? Try to help them get involved. Get owner representation. Push for an owner representative to work with you all the time. That's a really good way to get them involved, to care. Often in the building world, we have an architect that designs it, hires engineers, and then they hire general contractors and say, okay, here's your building at the end. You know, the owner has the keys at the end. That's basically how that works out. So I'm jumping around a little bit. We talked about commissioning the building, the fundamentals of commissioning. Now we're going to get into the automation side. What do we have here? This is just a schedule layout of a building. This is a heat pump building. We have various areas, band room, cafeteria, energy recovery units, and some various other things. I would say most buildings, when they are built, they have all this stuff smashed together in one schedule. Makes it pretty easy to change the schedule, right? Well, what happens? All that equipment starts at one time. So that causes a lot of consumption, a lot of demand, a lot of wear and tear on the equipment. So first things first, we say, okay, how do we limit that? We take that one schedule and we make a whole bunch of schedules. Now we've got different parts of the building starting at different periods of the day, right? And in a heat pump loop system, you really don't want to start everything all the time because it will impact the ground source water loop. So another component of this, what's this little guy right here? This area A classroom starting at 7 a.m., what does this guy mean? Optimal start, right? So why is that important? Optimal start is an algorithm that runs in the background. It looks at your outside air temperature, looks at your space temperature and your set point. And it determines how long in this 2-hour period I can start. If it's a really cold day in the wintertime, he might start at 5 a.m. to get comfortable by 7 a.m. Now, optimal start is not a new concept, but you'd be surprised how often I see it ignored. So typically what you would see, the building operator would say, I need my building warm by 7 o'clock. I'm going to start it at 5 a.m. every day, no matter what the outside air temperature is. This gives us the ability to let the computer do the work for us. Optimal start decides how early it needs to start to get warm by 7 a.m. every day. So we've done a couple different things, right? We spread out all the schedules, so different parts of the building start at different times. We've used optimal start, and we use a staggered start. Why is that important? The optimal start's going to make the decision, right? Well, let's say that our whole building starts a regular schedule at 7 a.m. with a 2-hour optimal start. On a really mild day, everything is going to start almost at 7 a.m. On a really cold day, on a design day, everything's going to start at 5 a.m. So we still have to do a little bit of math there and think we still need to offset these guys a little bit so they don't all start at the same time. So we talk about data commissioning. This is just a rooftop that I picked out. It's got some energy recovery. It's got a couple fans, exhaust fan. The key here is this particular piece of equipment has 45 data points. As a commissioning guy, I'm going to functionally test this piece of equipment. All this data, there's probably 30 different testing scenarios for this piece of equipment alone. Let's say there's 40 of them in that building. Wow, now that's tough, right? So functional testing, commissioning, is that right there. It's a snapshot in time. Let's say I'm there in August. I'm probably going to get the wintertime or the summertime, right? I'll be in the heat. But I'm not going to test the wintertime operation yet. I'm going to come back and try to test that, right? But everything in between, I don't know how it's operating. So the thing about commissioning is it's absolutely necessary to do. We all have to remember that it is a snapshot in time. You do those functional tests, you record how it works that day, put it in a book, and that's where it stays. So we use data analytics. All that data, all these points, all those 45 points times 50, all those hundreds, thousands of points. What do we do with that stuff? We use analytics. We let the computers do the work for us. Now there's a lot of stuff going on here, but the takeaways here is the equipment. We have a heat pump and approximately 4 rooftops there. On the left-hand side, we have just a small sample of some analytics, some algorithms that run in the background that say excessive runtime. That means that this piece of equipment ran for 24 hours. In the HVAC world, really, if it's not a hospital, if it's a school, there's really no reason to run anything 24 hours. So we say, okay, we're going to run this algorithm. Anytime a piece of equipment runs for more than 24 hours a day, we count 1 time in a day. That's what these guys mean. So my evaluation period on this particular building, and you're going to see a lot of examples where I just pick stuff out of reports that I did. So if I get off track, please ask me. So what this means is this guy ran for 76 days out of 100 days. You get a check mark per day. Green means good. No analytics were ran. And you can see that the average and worst offenders there. So we have some other things here. Ineffective primary cooling, outside air relative humidity accuracy, outside air temperature accuracy. These are pretty big. Now normally, we would have an outside air temperature and humidity that we would just communicate to all the equipment. Now, most of the time, this equipment has its own unit-mounted temperature and humidity. This makes a pretty big deal right here, and we're going to see this in a little bit as to why. Cooling set point out of range. That particular analytic means that anytime a space temperature is at 71 degrees cooling or lower, we deem that too cold. Most equipment's not designed to run below 73, 74 degrees. ASHRAE says 75. So that means that 45 out of 110 days, this heat pump was at 71 degrees or below. That's how we break down these charts. Now this guy could happen 100 times a day. I don't care. I just care that it happened 1 time and it checks off 1 day. So 45 days out of 110 days, that guy was triggered. Analytics run 24/7. Commissioning is a snapshot. Analytics is all the time. I don't have to worry about it. I just come check my charts, and there they are. So, now I'm not going to get too deep in the weeds on this particular guy here, but basically by looking at the analytics, I knew that this guy was running 24/7 at that time of day. I knew exactly when it was changed. I could go back in the audit log of the controls, and I knew exactly who changed it. Same with this guy. That guy was running since that day, 8/17/17. Same deal. I knew who did it, when it was done. And actually, this one here, this particular customer, every time they made a change, an override, it was recorded. So let's say I'm coming in a shift later. I want to know, why is that rooftop overridden? I can look and say, okay, Jim overrode this, and this is why. So that's another thing that controls can do for us. They give us an audit trail as what has happened in the past. Now, I was talking about outside air temperature and humidity accuracy. All these guys here talk about economizer. Economizer is using outside air instead of using a compressor. if it's cool enough outside, why do we need to run a compressor? These two guys here, excessive runtime and economizer, are the biggest energy hogs in a building. So when I talk about scheduling, and I put it first, because that's the first place we look. You can't get more efficient than shutting it off, right? So this is an analytic that looks at outside air temperature compensation or comparison. It looks at the outside air temperature reference, and in this case, it's actually one that's attached to the building. And these are standalone units that make their own economizer decisions, meaning they compare the inside air with the outside air and say, I want to use fresh air as opposed to compressors. And in this case, we look at all these units. They look pretty close to the same. Well, why is this guy, this RTU4, why is it warmer? Some time of the day, sometimes it's not, right? That's the daylight hours of the unit. And why is this important? Because this guy, it thinks it's warmer. It's using a compressor when all these other units are using outside air. So it's using energy when it shouldn't be. It's actually the sun. On this particular unit, the sun was hitting the side of the unit, causing it to heat up the sensor, causing it to run a compressor when it wasn't supposed to. Did the math, and it was like a couple $1,000s a year, just because the sun was heating up that sensor. So that's why it's important to understand these little nuances of a building. In this case, what we did is we took this guy and we just wrote it to all the rooftops and saved them a couple $1,000s a year. Pretty easy deal there. So let's dig a little deeper on these analytics. Now, before I showed you just a few of them, here's some more. I'm not going to get in super deep of these because we already talked about this, but let's pick one. Let's pick RTU3. In this case, 69 days out of 87 days, RTU3 was struggling to maintain duct static pressure. So, charts and graphs, that's what I do. I love it. I know it drives some people crazy, but it's what I do. So, we're talking about RTU3 supply air pressure control. On the left is duct static pressure. This is what the rooftop's supplying to the VAV boxes. This gray area is unoccupied. And when you look at this chart, you can always tell unoccupied typically by a flat line on the bottom. So for conversation's sake here, I put some arrows where they're unoccupied. So let's take those guys away. Every time this unit's occupied, it never maintains duct static pressure. There's actually a reset in the unit. It's called critical zone reset. And I'm going to show you a little bit about that here in a second. But basically, it resets the static pressure set point of the rooftop based on all the VAVs. If one VAV needs more air, it's going to start bumping up the set point to make it happy, basically. There's roughly 13 VAV boxes served by this unit. It's recommended to evaluate test and balance. What is test and balance? It's a technician that comes in at the end of the building and tunes the building up, basically. Because when we install it, everything's wide open. All the air dampers are wide open. This particular room could be served by the same amount of air as that particular room. He comes in and he balances everything out so it makes the capacity of the equipment work. Typically, I always enlist a test and balance guy when I'm evaluating building, just so I know what's going on, air side or water side. So, critical zone reset. Other terms for that, VAV optimization, duct static optimization. Basically what that does is it gives the ability to have capacity control. Let's say our rooftop unit has the ability to supply 20,000 CFM at 55 degrees all the time at 2 inches static. What if it's a nice day? Our VAVs aren't that busy. Let's move that rooftop down a little bit to save some energy. The same way on a design day when it's hot. We can reset the air up to make them happy. Gives us the ability to turn it down. So what we have here is we have a chart, and on the left here is a VAV damper position. I drew a line at 75 and I drew a line at 45. This is the damper. As it's moving through, the damper is going to move back and forth all day long to satisfy a CFM set point, the air that is supplying to the space. Now, any VAV box that's served by that rooftop hits 75%, I'm going to move my set point up, my static air set point up. Let's say I start at 1 inch. I'm going to move it up by 0.1 inches over a 15-minute period.
Bless you.
Thank you.
As I go down, if all the boxes are happy, they drop below 45, I'm going to take my set point and move it down. The whole point of this is to keep the VAV boxes operating in this area. Middle 1/3 is where we like it. Y'all remember the analog gauges? Seen pressure gauges all the time. I'm sure everybody's seen one. Believe it or not, the most accurate place for that gauge is in the middle 1/3. Same way for a VAV box, air damper. They like to stay within here. So these set points can be really anything depending on what the balancer says, but as long as we stay right in here, we're going to get the best control. It's not going to be noisy. Look at this graph. Man, I should have toned this one down, Robert. Anyway, the takeaways from this, forget about all this stuff. We don't care about any of it. All we care that this is a damper position. Same type of thing I just showed you. 0 to 100. Gray is unoccupied. When the unit goes unoccupied, all the VAV boxes listed here, this is their damper position. And this is the average of the boxes. And we have a control range, right? We talked about that middle 1/3. We want to keep it right in here. So there's the average of those boxes. They're kind of jumping all over the place, right? All we really care about here is these guys right here at about 10:30 during in the day, they all go to 100%. They're now starved. They're not getting enough air. So what does that do? It tells the rooftop, I need more air. So it keeps resetting the air pressure up and up and up. The rooftop goes to 100%. That's it. Now we're at full capacity of the rooftop. So what does this tell me? This tells me right away that I need to look at these VAV boxes. I need to get a test and balance guy and say, why are these VAV boxes so starved? There's something else we look at, right? Is these VAV boxes are at 100%. Well, what are these guys doing out here? Some of them are shutting off completely. They've got too much air. They're below that lower control range. So we've got two things going on here. We have 4 VAV boxes that are completely out of control. They're not getting enough air. Their space temperatures are failing. And then we have a whole bunch right here that have air to spare. When you get below this lower control range, they don't control very well, and they're noisy. Very often you'll be in an office where you'll hear just air screaming. It's probably not even coming out of the diffusers. It's probably coming out of the VAV box. So there's those VAV boxes. Boxes that operate below their control range don't control very well. It can be noisy. Okay, so I'm trying to squeeze as much in here as I can. I see I'm running out of time. So energy, that's what we care about, right? Why do we, what's that?
You're running until 7:30.
I got a lot of videos and stuff to show too. So the thermal imaging is the cool stuff. This is all boring. So energy, why do we analyze it? Benchmarking. We need to know where we started if we're going to save energy. We all get those utility bills, right? Now, where do I get the data? Do I get it from utility bills? Gas, electric, water? Do I get it from an on-site installed meter, which is becoming more and more common? Lots of engineers demand it in their design documents. We need to install these meters. And then the automation system will talk to them. Well, that's all fine and good, but what do we do with it, right? This is what we get right now. Yes, sir.
Sorry to interrupt you, Doug. Are you going to get back and tell us what the punchline is on those 4 VAV boxes?
Yeah, I can. That's good. That's the kind of interaction I like. I forgot my candy bar. Sorry, bud. So what happened there was this was actually an older system that had duct liner in it. Duct liner is insulation that's on the inside of ductwork. We don't like to do that anymore. What happened was there was a branch duct that went out that fed these 4 that fell down and blocked the ductwork. Now, 2 of these VAV boxes were actually satisfying the space temperature. So if we didn't have the analytics, we would have never known that these guys were causing this issue. The whole idea, and thank you, Robert, for bringing that up, is that they use the analytics to find out that it wasn't operating efficiently. Now, often equipment will operate and it will satisfy the set point. It could be running erratically. The space temperature set point could be going like this, but nobody complained. We never knew. The discharge air temperature could be really erratic. We never knew. But the analytics now let us know, yes, the equipment is satisfying the space, but it's not doing it efficiently. It was causing that rooftop to run at 100% all the time. Back to energy. So this is what we all get, right? We get our monthly bills. We get our bill here in December. Heat pump. We're like, wow, that was expensive. Gee, I wonder what happened there. You get to look backwards, right? You never can look forward. The power company certainly doesn't care. So let's take that interval data, that 15-minute interval data we get. It's like resolution on your TV. I don't want to watch a TV that has 12 pixels. I want to watch one that's got 35,000 pixels. So that's the difference. It's resolution. We now have the ability to get all this data. Why is that important? It gives the ability to see exactly what happens and when. So this is what we call a spectral analysis. Basically, we're taking all that data points and we're putting nice little colors. It makes the data easy to read, right? So on the left here, we have time of day, and then across the top, we have days. And you can see we have Monday through Friday. This actually is school. So we can also pick out days that should have been scheduled off. In this particular school, there was a teacher in service that was in one small part of the building, but they had the entire building occupied. So in this case, it was the entire building was occupied, but there was no load. No teachers or students. That's a lot of money that went out the window right there that we could have easily fixed. And this is where you can see they changed the equipment schedule. They were going until approximately 9:30, and then they changed the equipment schedule. And down here is real time. This is 15 minutes ago. So it really gives us the ability to see real time what's going on. I can analyze everything. I can see that I've got equipment running in the evening. I can see that my optimal start's working. Today things start a little earlier. You can see all the way across here. This is a little warmer day, so start a little earlier.
Oh,
Go ahead.
so that's just using utility data, no BAS.
This is BAS.
Oh,
Yes.
it is BAS.
Yep. This is 15-minute interval data. This is utility data, and this is our interval data. Sorry, 15 minutes. Now, I generally do 15-minute intervals, but if you have an automation system that's getting it real time, it could be instantaneous, right? If you have a Jace or another controller that has a meter to it, those data logs can be instantaneous. So you could simply turn a machine off to see what your KW reduction would be. Easy as that. Now, this is another instance of using that data. Now, in the olden days, a couple years ago, I was doing all this stuff manually, right? All the charting and spreadsheets, I got really good at spreadsheets. Now we let the computers do it, most of it. You still have to mine through it all and figure it out. So what this does, this is an off-hours load analysis. The blue is our expected KW usage, expected demand. And the red is unexpected. In this case, there was a chiller cycling over the weekend for no apparent reason. A relay had frozen, basically. And the potential savings for that were pretty astronomical. Not only in just electricity, but maintenance. You reduce the starts, you reduce the maintenance costs. And you can see the change in just replacing a $2 relay. Analytics helped us find that. Into the thermal imaging. Any questions on any of that stuff I just covered?
Yeah, the deferred maintenance, how do you derive that?
That was from Daikin. They just said if we reduce the chiller starts by X amount a year, we get $30,000 in deferred maintenance. And this was, I work for Trane, but I called Daikin and they gave me that number. Yes, sir.
And like expect to see the chiller. Yeah.
Starts is huge.
And what was the solution for the unit that was being overheated by the sun?
Oh, that was what we did there. We'll go back a little bit here.
Said you used the global depth.
Yeah, we used
global
the,
outside air.
get back here somewhere. Okay, so what we use there As you see this, I don't even know what color that is. This outside air temperature reference, this was actually one that was mounted to the building. When the building was built and commissioned, each individual unit had its own economizer control. So all we did simply there was take this outside air temperature that followed pretty closely with the rest of them that told us, we could go ahead and use that one and exclude that guy. That's what we ended up doing there.
Exactly as we're doing in the lab tomorrow for our outside air temperature reference.
Any questions on the analytics?
So are y'all doing a lot with, like fault diagnostics and checking for leaking
Yes.
valves and doing the math to,
Yeah, so a lot of those analytics that I showed you, those counts, if you will, those are just a small number
yeah.
of the analytics that are generated.
Right.
A VAV can generate 35 or 36 analytics, and it shows, it does things over time based on all these variables. It says yesterday it performed this way, today it's performing this way. It doesn't meet our algorithm.
Right.
Space temperature is the same way. Ineffective cooling, ineffective heating, overheating or overcooling. There's so many analytics that run there that in the background.
The fault diagnostics kind of pulls that together, looking at it as in terms of habit.
Right. Pattern recognition is a big thing. So obviously the longer a piece of equipment runs, you get more history, more data. Any building, 5 years old, probably needs looked at. Sensors, drift, spaces, walls, windows, all these things affect them. So if we get a fault from a piece of equipment, yes, that equipment faulted, but it might be due to something completely different. So you just kind of have to follow. And the thing about all this stuff, you're never going to replace a tech in the field.
Right.
They still have to fix it. They still have to mine through all this stuff and decipher what needs to be fixed and what doesn't. Because I could look at one of these and send a work order out, and the guy could say, well, the reason it failed is because somebody left a window open. I just rolled the truck because there was a window open.
I think when we say energy management, that's probably the biggest miss. I mean, we think of utility bills, but the real energy management is saving labor.
Yes.
When you've got to send a guy in the field to check on 3 things that are completely irrelevant, and you've only got 3 guys and 50 things to look at. That's where the
Yes, automation
pattern
systems.
recognition is so helpful.
Yeah, automation systems, analytics, use all those things together to save those truck rolls. And if you can fix it remotely, or even save that tech an hour on the phone. All right, so thermal imaging. These are just a few of the applications: mechanical, electrical, piping, insulation, roofing, envelope, windows, whatever, you name it. If it transfers heat, you can see it. And I do heat transfer for a living. So I wish I had this thing in my truck 20 years ago. It would have saved me a ton of time. As a matter of fact, I published an article in the HVAC News on why everybody should have one in their tool bag. I'll show you that at the end.
The $50,000 ones or the?
Yeah, you can buy them for your phone now. They're a couple $100.
Yeah.
That's never going to replace the resolution of a $50,000 camera. So this was taken with a $50,000 camera.
Yeah, right.
So this is a mechanical room. A few things going on here, right? I've got 2 boilers, 2 condensing boilers. I have a supply line and a return line that are doing heat injection for a heat pump loop. You guys are from all over the place, and I don't know what kind of equipment you're used to, but here in the Midwest we do a lot of heat pumps. We do typically ground source, and we do heat injection, and sometimes we have a cooling tower. It really depends on the designer, how they want to do it. They are super efficient. Pay close attention to this valve that was installed right here. Now this is a video of what's happening here. This boiler is lead boiler. This is a lag boiler. It's coming out of this boiler, the supply, and it's circulating and going back into that boiler. Because there was a valve installed over there that I showed you that was open. Actually, there was no valve installed. I had them install that valve. So the water is coming out of the heat pump loop and It's kind of sort of being injected, but not really. Now, since the first boiler didn't do it, the second boiler started. Owner never knew the difference because their heat pump loop was getting the heat injection that they required. That's another thing. Yes, it was heating the building up. It was injecting heat. But it was using 2 boilers to do it, and that boiler isn't heating anything but itself, right? It's doing a really good job at it. That's some of the power of thermal imaging. Now, I close that valve, and you can immediately see the cold water going to where it's supposed to go.
So this was a retro commissioning job?
This was actually a new job, a new construction. Yeah, you can see the valve closed there. I'm not sure why they installed it, or why they left that bypass in there. But you can see the cold water going into the return of the boiler like it's supposed to. And they fought me on it until I showed them this. They're like, okay, that makes sense.
4 o'clock and the 6-pack of beer was in 30 minutes.
Yeah.
They're going to get out of the job site.
And his boss actually came out there, and he ended up going and buying a thermal camera the next day.
How much was the one that you took this picture with?
It was approximately $50,000.
Yeah.
Oh, this is a high dollar.
Yeah, this was a FLIR T620.
Yeah.
So I use an E60, which is about $4,000 or $5,000 most of the time, because I can drop it, and I'm pretty clumsy. You drop that T620 one time, it's like, whoa, I'm done for the day. I'm going home.
Confession.
Now, look what's happening here. The water's actually going back this way. The 2 boiler pumps are actually overtaking the system pump, because the system pump is variable speed and the two boiler pumps are constant volume. Heat is still being injected, but the boiler pumps are starting to suck it back this way. So our test and balance guy ended up taking care of that for us. So it's a motor. This particular project, I was commissioning a water treatment plant, and I was there for something completely different. But the beauty about thermal imaging, we see what we want to see through the camera. We can't see it with our naked eye. So I take it everywhere. Any building I go into, I take it with me. And a guy I work with a lot, I talked him into just buying the $300 one that he can put on his iPhone. He uses it every day, all day long. I know Cat makes one that's all interconnected now. You can buy the cell phone that's got the FLIR technology in it. So this is a view of that particular motor. Brand new motor, by the way. Contractor demobilized. Now, forget about this for a second. This is a typical motor temperature profile. You've got your heat in the middle from the windings, and on the other side you have a cool bearing. Bearing shouldn't produce heat. And then you've got this bearing. Man, it's really messed up. This is a brand new pump. So I asked the contractor, what do you think of this pump? And it was actively making noise. An electric motor is going to tell you it's failing. It's going to tell you it's failing by making noise or producing heat. And in this case, it was doing both. So I was in the mechanical room doing my thing and looking at some piping, and I heard it. And I shot it, and I knew. So the contractor ordered in a motor, brought it out, replaced it. This particular water pump was doing water pressure for a small town. It was the only one, no redundancy. And the lead time on the particular pump was 2 weeks. So by the time he got there, that pump was almost shot, but the city didn't lose their water.
How much did you charge for that photo?
Nothing. I was there doing commissioning. It's just you're working for the owner. Whatever you see, whatever you can find, it's helping you out.
How long would it have been before that failed?
It's hard to say. So you can actually do the math, and these motor manufacturers can tell you exactly what these temperatures are supposed to be. If the winding temperature, if the jacket temperature is X, the winding temperature will be Y. With a bearing, it's hard to say what temperature finally caused that bearing to seize up, or it started transferring heat into the windings, melted the jackets on the wires. It's hard to say. A couple weeks maybe, a month. With bearings, you just never know. Murphy would say the next day, but You never know there. So another application, steam systems, huge heat transfer. It's really easy to see issues in steam. So this is a radiator. We've all seen radiators before. What temperature is steam? Anything above boiling, right? So in this case, it was 232. What's that temperature right there? About 89 degrees. So in a steam system, the little guy down here separates the steam from condensate, right? So this guy was really waterlogged, and when you get steam mixing with water, what do you get? Flashing, noise. That was the complaint. The owner was like, why is it, it sounds like somebody's upstairs with a hammer beating on my pipes, right? It was this guy right here, because it had steam and cold water together flashing and literally exploding. So sometimes if you get into an old building and hear that banging noise, that's exactly what's happening. So this is an elementary school with spray foam insulation.
What was the solution on that last?
On this guy, replace the trap. Yeah. Steam traps are actually, I use thermal imaging and ultrasonic because you can, with the two together, you can really pick out a trap if it's going bad. Foam insulation in a building. It went ceiling to floor, but the foam insulator, I don't really know how to say, he was very, very short. So as he started getting closer to the ceiling, it got thinner and thinner and thinner. I'm not very tall, so I guess I can say that. But you can see, you can kind of see where it started to dissipate. And there was already drywall here. So that cost that guy a lot of money, because not only did he have to pay for new drywall, he had to pay for new insulation. And the district I was working here for, they will not let you cut it out and just spray over it. For whatever reason, because they always see a gap in there where the materials are different age. Apparently the foam makes a difference. Another insulator, different school, same type of deal, but this one is different than this one. This one was a gap in insulation. This one was wet insulation. You can kind of see how the water was running down, and it's a totally different profile than this guy. You can see the edges of this where it was a gap. Here, you can't really see the edges. It just starts to be a gradient and blend in. That's a sure sign of water. So what happened was there was no flashing on that side of the building. It rained. Unfortunately, they decided to do the drywall and insulation before they put the roof on. I have no idea. So here's another application, ductwork. These guys here, these are two VAV boxes with electric reheat. Just like we talked about, a rooftop VAV system feeding VAV boxes. Complaint here was the units were running at 100%, couldn't figure out why, the balancer was out. He said everything was perfect.
It always is.
Yeah. And coincidentally, his balance report, everything ended in a 0. For whatever reason, all even numbers. So, what do we have here? Black is cold, red is hot. We've got a couple different things going on here. So, go back to this elbow, kind of see it. They didn't put any sealing compound around the elbow. They insulated over it. Once you insulate over it, it's really hard to tell, but you can see air actively leaking out of the ductwork. And not only that, but these were actually VAV boxes that were faulty from the factory. We actually found that they were leaking from inside the box. But this guy here, it was starved for air. It was the air was flowing in such a way that it stratified inside the duct. As you can see, cold air, hot air. This guy was tripping out on overload all the time. They couldn't figure out why. There wasn't enough airflow. And it turns out we found out that the installer had the same problem and bypassed the safeties on the VAV box.
Always a great idea.
Yeah. So we found numerous different things here. 1, poor ductwork installation. 2, faulty VAV boxes. And 3, somebody bypassed the safeties. Yeah, could have burnt the place down.
And you can see the conduits hot as well.
Yep.
We've been running for a while.
I used to do quite a bit of hotel work, energy audits, commissioning in hotels. This one particular hotel is in Boston. I wish I would have taken a better picture of this. So you kind of have to imagine that this right here is the check-in desk. You can kind of see the desk right here, and there's a mirror. This little door here, right behind it, is a valet shed from the outside. This is the middle of wintertime. And they had just replaced the heater in this particular valet shed because they were getting cold. So I took a picture with my thermal camera. I wasn't looking for this, but I was walking around. And I thought, wait a minute, this isn't right. So what happened here, what happens when you put too much load on a circuit? It turns into a heater itself, right? And that's exactly what this wire was. It was heating up the wire itself, the green field, and the drywall. And you can even see the studs were getting heated up. Can you see through walls? No. The movies are wrong. You cannot see through walls, no matter what anybody says. But what you can see is you can see secondary heat sources. The wires were heating up the insulation, which was heating up the wall material, which I could see the heat transfer. The terminator cannot see through walls. Secondary heat transfer. Why is that important? What if I'm looking at switchgear? If I can look at a switchgear with my thermal camera before I open it up, whether it's 480 volts or 15,000 volts, I know right away I don't want to touch this because it's hot. It's hotter than it should be. I'm going to call somebody that can fix this for me instead of opening the panel and getting an arc flash, you know. So, in conclusion, any questions on any thermal stuff, by the way?
Was that all the $50,000 camera, or was some of that be less expensive?
That was the E60 right there. Can you tell the difference?
A little less.
A little less resolution, yeah. Now, I give presentations on thermal imaging quite a bit. Let's see, which one was I going to show you here? Okay, so this here was also taken with the E60. See that little guy right there? That is the average, the spot size ratio. So think about a camera. If you're this close, the resolution is going to be higher than it is across the street, right? So anybody seen of those laser pointers, the laser temperature meters or whatever? That is 1 pixel. The further you get away, you get an average. Yeah, and you can't see what it is with that, but that's what happens. It's the same way with the thermal camera, except instead of having 1 pixel, you've got 300,000 pixels. So what that does, instead of, if I was standing that far back with one of those spot pyrometers, my average would probably be this big. So with the thermal camera, it shows you what your average is, okay? So as you get into those more expensive cameras, you get a lot of tech with them, but you also get more resolution. The T620 that I was using, you can barely see that circle because it's so finite. It's a 680 by 240 resolution, where this one's a 60 by 80.
But you can still see the hot spots.
Exactly.
That's
You can. There's a difference.
The problem is when you're averaging, you may not really see just how.
The thing is, though, let's go back to this motor. Let's go back to this motor. Now, this is with the T620. You can see the averages are super tiny.
Oh, so it wouldn't.
Yeah.
Okay.
So this is the E60. See the spot size on that one compared to the spot size on the T620.
So
More resolution.
Okay.
But it's more of a qualitative review anyway in our field.
Sure.
Do I really care what the temperature difference is between these two? No. I know it's hot. You're going to get nearly the same picture with a cheaper camera because you don't care what the temperature difference are. Qualitatively, you know that it's hot. That's really all we need to know, right? Do I need to know what the temperature delta is? Maybe, if I'm doing a quantitative comparison between these guys. If I'm trying to calculate what the insulation is doing, then maybe I need a higher resolution camera. But for all intent and purpose, if you're doing that qualitative view to see the differences, you don't really need to have it.
Those 4 spots.
What's that?
I didn't pick those 4 spots.
I did.
You did.
So I'm kind of a FLIR nerd. Their software does amazing things. I take these pictures and I take them back to my computer and I analyze them. Tune them, put spots on them, do whatever. Do a lot of tech with that. So I give presentations on thermal imaging that are approximately an hour. And we really get into why thermal cameras work the way they are, and spot size ratio and all that stuff. And I'd be happy to set up webinars to do some of that. So, any other questions? Conclusion. Going to kind of throw everything together here. Commissioning authority, engage the owner and controls the vendor early in the project, early as possible. Analytics are ever increasing. It can be used as another tool to aid troubleshooting and repair of equipment and systems. Never replace the technician. You're always going to have a tech. And unfortunately, as you all well know, they're getting old. I'm getting old. Robert's getting old. We're all getting old. Analytics will never take the place of a technician. Thermal imaging cameras are affordable and easy to use. And the important thing, one of the very important things about thermal imaging I didn't put up here, is that it is safe. You don't have to touch anything. The old days where you had a meter and a thermistor to touch something, don't need to do that anymore. You can do it with thermal imaging. So this is an article I wrote and published. Why do I need a thermal camera in my tool bag? This is my website. Robert will share this stuff with you. On my website is kind of where I put a lot of my thermal imaging cases. I only just showed a few of them today. I've got 20 or 30 on there where you can go and see exactly what the story was behind the picture. Questions?
Can you go back to that?
Sure.
Thank you.
It'll be on the Google Drive as well,
Are you sharing the PDF?
if that's all right with you.
Yeah, it's fine. No problem. There's no proprietary information on there.
Can you talk a little bit about the process that you go through when you set up the analytics, you know, with you have 20 rooftop units or 35 VAB boxes? I mean, you get a lot of data points, but there's a lot of labor involved in setting up those
It does. BACnet has helped us out quite a bit with that. The biggest thing is normalizing data, right? A space temperature is a space temperature. In traditional, let's say that I take any project, I want the data out of there. I can do it one of two ways. Typically, I'm going to put a box on there, and I'm going to take all these data points in your system, and I'm going to make a match in my system. Mapping points, right? Space temperature, set point, whatever it is. BACnet has really helped us, Asher has really helped us by normalizing that data for us, saying that your space temperature is going to be this variable, and it's going to be close to this name. So that pattern recognition and that naming recognition, lots of times you can dump those points into an algorithm, let it run, and it's going to figure out what those are. And it's going to match those points up for us. So traditionally, you'd have to map all that stuff. And you still...
Blonde.
It's another story. So there's still some mapping involved because not every point matches up. Some vendors have a supply fan status that isn't binary. It could be a multi-state value, which means that a number means something. And that certainly helps us do that. Now, a lot of times the algorithms that are written, we kind of try to paint a broad brush with a particular piece of equipment. A rooftop, for example, all the algorithms that we have are going to kind of fit that. And then there is a period of time where we need to evaluate that data. Is it real? Are those analytics that are generated, like I showed you on the charts, are they real and do they mean something? And then as we do that, over time, the machine learning will take care of some of that. But for right now, you got to do a lot of that stuff yourself. And I think everybody's kind of in that place. We're slowly phasing ourselves out, I think.
Is the stuff y'all are using Trane proprietary? It works on y'all systems, or y'all doing it on your system?
There's a lot of folks that are doing data analytics now. So it's what you do with the data, how you do it. I really don't want to get into vendor-specific things, but a lot of Trane stuff is plug and play. Most vendors are doing that. If it's a Johnson piece of equipment and it's Johnson tech, they're going to talk to each other. I mean, that's kind of everywhere. They do that. Mm-hmm. Yes, sir.
Could you go back one slide there?
This one?
Yes. Can you talk about the third bullet a bit?
This guy here?
Yes.
Sure. So all that data, when I analyze that data, I've got to analyze it. So if it goes out and as an owner you have this mountain of data, you still have to look through it. You still have to decide, is this viable data? Did somebody leave a door open that was causing this analytic to generate? So as far as technicians go, in the foreseeable future, there's always going to have to be somebody analyzing this data and saying, you need to roll a truck and you need to go fix that, or you need to fix it remotely. Where a technician looks at this, first place he goes is the automation computer. Looks at that piece of equipment, looks at the data and says, okay, I have a pretty good idea what I need to do to fix it. We're not in a place where a lot of this stuff is completely AI, and I'd really be surprised if it ever gets that far. You're never going to get away from turning a wrench.
I've been out there with people that have slapped trends on equipment that wasn't working while we were looking at it. What do you want to trend it for? It's not working now.
Yeah, it's all what you do with the data.
So you won't come, Mark, you asked for a lot.
Let's fix
But
it.
it's
We can
also
trend
to
it.
prioritize.
Hey, Mark, you have to do it because when you tell the owner or the guy that's supposed to keep it running, he won't believe you unless you show him a trend that says it's not running.
I can,
Baseline.
I can manufacture
So,
those in a minute.
A lot of some of the higher echelon control companies now, they will do a lot of remote services prior to rolling a truck. High revenue, and it saves the customer money. If we can fix it in an hour in the office as opposed to driving 2 hours there and back and charging them for that. So the customers are really starting to demand a lot of this technology. So if they don't get on the bus, they're going to miss it. Yes, sir.
You guys have your energy center set up here? Are you local here?
Yeah, I'm here in Omaha.
Yep.
Yep,
Because,
you can.
in Chicago, they have their own whole energy center with the new, obviously, green brand that you guys are going with, as opposed to the orange. And that's exactly what they do.
Yep, we have intelligent services set up here in Omaha, and we do most of the Midwest actually. Any other questions?
What are you seeing with regard to IoT and the proliferation of sensors?
That's a very good
Data?
question. So there's two terms that we use quite a bit in automation: integration and interoperation. It used to be, if I wanted to hook something up to my control system, I would hook sensors up to it, or I would hook a communication link up to it. And then as an automation system would then communicate with it, get data, send it data, whatever. That's integration. It does its own thing, but it has no interface. Its interface is your automation system. Interoperation is something that has its own mind. It has its own interface, but we talk to it. A fire system is a very good example of that. It stands alone, it has its own system, it does its own thing, but we can still talk to it. Interoperation, it's operating, and they're kind of talking to each other. So as far as IoT goes, it's infinite right now. Everything is talking to everything else. You can't buy a refrigerator now without the guy saying, you know, you can talk to this with your phone? Or you can see the front door from your refrigerator? I'm like, I can already see it from my phone, but thank you. Did that answer your question? IoT is never ending. And we're getting to a place where it's almost moving into a plug and play situation. Happy you took your laptop down. I wasn't sure if I was going to be able to see over it or not. If there's no other questions, we're out of time. So if Robert and I can offer some webinars at a later date, let us know. Sorry, Robert, I suppose I should have asked you first.
You already knew the
Thank you. Appreciate it.